Join me for an overview of the Series B MSO, which has a stunning 15.6-inch high-definition capacitive touch display and a user interface that's been designed from scratch to be optimized for both touchscreen interactions and also traditional button and knob control. Available in 4-channel, 6-channel, and 8-channel configurations, with bandwidth options from 350 MHz to 2 GHz. You can capture fast edges with rise times as quick as 225 picoseconds, making this the perfect oscilloscope for use across many applications. A variety of record lengths are available, from standard record length of 62.5 million points per channel to up to 500 million points per channel. This means you can capture an 80 millisecond acquisition at maximum sample rate. Like most other upgrades, you can add record length at any time in your lab without sending your scope to a service center. The heart of this scope's acquisition system is the Tektronix proprietary TEK49 analog-to-digital converter. This ASIC enables 6.25 gigasample per second sample rate, even when all channels are active. The TEK49 ASIC delivers 12 bits of vertical resolution for excellent detail, even in the presence of large signals. By turning on high-resolution mode, you can go up to 16 bits of vertical resolution, which takes advantage of oversampling while controlling noise through advanced filtering. The Series B MSO also integrates functions common to digital voltmeters, protocol analyzers, trigger frequency counters, a 100 MHz function generator, and spectrum analyzers. Each of the 8 inputs automatically detects which type of probe you've connected and gets you set up for analysis immediately. See here, when I disconnect a BNC cable and replace it with a logic probe, that the settings and display change from being an analog input over to 8 digital inputs immediately. A wide range of probes are compatible with the TEK VPI probe interface, including passive probes, single-ended active probes, differential probes, current probes, optically isolated differential probes, power rail probes, and more. Compensating probes is an important step in ensuring that signals aren't becoming distorted and your measurements are reliable and accurate. Simply connect the probe to the signal pins here over on the right side of the scope, and a few taps later, everything is optimized automatically. You can use the Series B MSO right out of the box with the embedded operating system provided standard. Or, if you want to run PC applications or automated testing on the scope, you can add a Windows operating system. It's one of the few instruments that allows this flexibility. There's also a low-profile form factor available, with nearly all of the same features and flexibility that we just discussed. At 8 channels, in a 2-rack unit form factor, it's perfect for when space is at a premium and channel density is critical. In this video, we're going to spend a few minutes looking at the Series B MSO user interface and some of the standard features that make it simple to operate and easy to master. The first thing we should talk about is menus. Rather than layering menus on top of each other, we have thoughtfully designed the placement of every user interface button, status readout, and measurement result. The Series B MSO incorporates the touch gestures that we commonly use on our phones, tablets, and other consumer devices. Turning on a channel just takes one quick tap. And setting up the horizontal and vertical settings can be done with pinch and drag gestures on the screen, or the front panel buttons and knobs. When you need to add a measurement, it's just a drag and a drop onto the channel that you're interested in. And there are dozens of measurements available. Each one has a summary image and description to ensure that you're adding exactly what you need at that moment. When you only need the measurement to apply to a portion of the acquisition, you can use gating. Here we will gate so that only what is in between cursors is measured. Watch as we move the cursors and the measurement results update. And once you're done with a measurement or a channel, just swipe it away and it's gone. By default, channels are stacked separate from each other to maximize the dynamic range of the analog to digital converter. And they can be overlaid to make it easier to visualize how the signals might be related to one another. It looks like there's some crosstalk here. Channel 2 is bleeding over into channel 1. Let's add a callout to document the conclusion that I have come to. We can customize this callout quite a bit. I'm going to draw a box, add text, change the color, and move things around. And when I save this screenshot or session file and come back to it later on my scope, another scope, or TekScope on my computer, these extra details will help me remember exactly what was going on during this measurement. You can also increase the user interface font size for when you need to sit further away from the screen. Or you can decrease it for when you need to maximize the waveform viewing area. A searchable help directory loaded on the scope is just a click away to give you information and assistance right when you need it. Let's look at some of the measurement and analysis tools that are helpful to 5 Series B MSO users who are looking for more features than a traditional oscilloscope might offer. First off, this scope has an advanced trigger engine that enables 10 different trigger types, which can be applied to all 8 channels. Surprisingly, not all 8-channel oscilloscopes have this same capability. Decoding serial communications like I2C, 8B, 10B, CAN, LIN, FlexRay is fast and easy. Add a bus decode results table and configure your view to view packet details and quickly locate and debug errors. Turning on history mode uses extended memory, allowing you to capture many trigger events. You can stop when you see something interesting and quickly review those prior events. We can also use Visual Trigger to easily construct complicated trigger logic. Simply draw a box over an area of interest and select if you want to ensure that signals enter that region or are absent from that region. You can keep adding regions as needed and update their settings at any time. Now, let's switch over to talking about measurements. In this example, I'm looking at a spread spectrum clock. It's easy to just drag and drop a measurement to determine the clock frequency and also include advanced statistics. And by adding a results table, we can view the measurement mean, minimum, maximum, and standard deviation for both the active acquisition and the entire measurement population. We can also add a histogram to visualize the measurement variation. And rearrange these views so that our screen space is optimized, and we can quickly clear away things when they're no longer needed. When you think that signal behavior has a repeatable nature, it's easy to add a time trend and confirm that assumption. Here's an example where a spread spectrum clock frequency is triangularly modulated. By using horizontal and vertical cursors, we can quickly determine that the clock varies from 97 MHz to 100 MHz in approximately 13 microseconds, with a period of 26 microseconds. And when you have a long acquisition, like this one, it's easy to zoom and scroll through the entirety of the recorded signal. And when you know what you're looking for, like a pulse width less than 6.24 nanoseconds like in this example, you can also use the search functionality to pinpoint and cycle through each occurrence that meets your criteria. Notice that each occurrence is marked with a pink triangle in the zoom window. And when you're looking for signal anomalies that fail either mask or limit test conditions, it's easy to configure and customize by either drawing a mask region or a limit test that's based on a golden waveform. Your scope can be upgraded at any time to enable capabilities beyond what we have discussed in this video. And those available options can be reviewed in the Help License Option menu. Testing and debugging embedded systems often involves looking for clues that can be hard to discover if you're only looking at a single domain. While correlating signals across multiple domains has traditionally been a painful and technically challenging process, Spectrum View on our 5 Series B MSO offers an incredible solution. Spectrum View uses patented hardware built into the analog-to-digital converter, which we call the TEK49 ASIC. Inside the TEK49 ASICs are digital down converters, which optimize analysis based on the selected center frequency and span settings. This analysis is a more computationally efficient way to display the spectral content of the signal, enabling best-in-class analysis and measurement results. This technology gives you the ability to independently control the acquisition settings for the time domain and for the frequency domain. And when we only want to acquire a few cycles of this clock, the traditional FFT in our top left corner doesn't have enough samples to provide meaningful data. And when we need to acquire a longer record, the FFT doesn't have enough sample rate to resolve these frequencies. Notice that throughout all setting changes, the Spectrum View display in the top right remain unchanged. It was not affected by our changes in the time domain settings. When required by my analysis, I have complete control over my center frequency, span, and resolution bandwidth. Spectrum View also enables us to look at the variation in RF magnitude, RF frequency, and RF phase as it relates to our acquisition timescale. In this example, let's turn on frequency versus time. It looks like this frequency is modulated in a triangular pattern. I can quickly change our hardware edge trigger to the frequency versus time waveform and stabilize this triangular wave. Adding a few measurements, we can determine the frequency deviation and period of the triangular modulation. It looks like the spread spectrum clock varies 3 MHz from our 98.5 MHz center frequency, with a period of 25.5 microseconds. Another capability is that each of these 8 inputs can be individually configured to view a different center frequency. Let's connect channel 2 to a 40 MHz clock to see this in action. Notice that channel 1 Spectrum View is centered on 98.5 MHz, and channel 2 Spectrum View is centered on 40 MHz. No matter how many channels we add, each can be configured to its own center frequency. We can overlay the Spectrum View windows to get an easier visual comparison to see interactions between signals. I'm not sure if you noticed, but every once in a while, the channel 2 Spectrum View signal seems to jump. Let's turn on the frequency versus time trace for channel 2 and configure a frequency versus time trigger on the channel 2 signal and lengthen our acquisition. Let's take a single acquisition. Okay, this rectangle is called spectrum time, and it allows me to select exactly which portion of our acquisition is represented in the Spectrum View window. See, as I drag spectrum time around, the spectrum view window is updated with the RF content derived from this exact time window in our analog acquisition. This lends itself to an incredibly diverse set of use cases, including EMC troubleshooting. You can even connect a near-field probe to one of these inputs and correlate power supply sequencing, serial communications, or active component behavior with your electromagnetic emissions. And when you're interested in more advanced RF measurements, you can install SignalView PC on your instrument, which will enable immediate vector signal analysis for measurements such as modulation analysis, adjacent channel power, spectrogram display, pulse analysis, and more.